Test. Test. Welcome to Bayesian Cognitive Modeling, where I, Keontae, learn how to do Bayesian inference by practicing all the exercises in the textbook, so I can prepare to implement, well, Bayesian inference across a range of appropriate research questions. I see myself as someone trying to become more of a hybrid sort of analyst or statistician, where I'm highly interested in learning about statistics and its application in my particular substantive domain, that being cognitive psychology. And I want to be able to use all the tools available to me. And part of a very powerful set of tools that is commonly used within this domain is the use of Bayesian estimation strategies. So we're here learning how to do it. Plus, it's pretty fun, I will say. Seems like I'm unlocking like a whole world of really unique ideas that I've been excited about and have heard as being potential solutions to some problems that are currently happening within my field of psychology. Those issues pertaining to replicability and, well, I would say on the statistical side, yeah, we're having challenges with the reliability of our findings, and part of what makes findings unreliable is their ability to replicate. And part of the issue with that is related to the conventional statistics used in order to publish results. I won't go on about this today because we're here to do Bayesian cognitive modeling, but just say I am highly incentivized to continue to learn how to use this particular strategy for approaching my research questions. So that's why we're here today. And we're doing the case studies. So we did the first case study yesterday on memory retention. And now we're going to move into signal detection theory, which is a theory that is, well, I'm not too familiar with, in part because I think it's slightly fallen out of vogue in psychology. I would say part of that is because the particular type of questions that one could use in order to that one would use this type of technique or theory have now been people have been testing other sorts of models, such as drift diffusion models or other sequential sampling model paradigms. So the thing about it is the sorts of data that you get from doing designs that would be appropriate to test signal detection theory also could be appropriate to test drift diffusion models or to test other evidence accumulation based models. And those models are currently, in my understanding, a little more powerful, but I'm not an expert yet, but I will be. So look forward to that. Anyways, either or, today we're learning about signal detection theory, and we're going to be going through the chapter together and doing the exercises. I hope to get through most of it today. I do have class at 3:30, so I'm going to be going all the way up until class. Looks like I'll have about an hour, 10 minutes or so so we'll just get right into it. We'll start by going through some of the background things needed or necessary to know when we're thinking about what parameters are going to be of interest to us in a signal detection theory framework. All right, so signal detection theory is based on this idea that, let's see, signal and noise can be represented unidimensionally, meaning that across a single dimension, we have strength being evidence here. And as someone answers a question, they're, in theory, referencing like some decision criterion related to what is representative of noise and what's representative of signal, I think. So the strength of signals are assumed to, on average, be greater than noise strengths. So that's one feature. In the standard model, we assume equal variance between the two signal and noise distributions here. So notice how this theory also fits nicely into Bayesian statistics, because we're going to get an output of a distribution for a posterior distribution for what is representative of signal here. And then from that, we're going to be able to estimate these parameters related to interesting things in signal. So D is discriminability. And if we assume that noise is centered on mean 0 and holds equal variance to that of signal, I don't know if the variance assumption is needed for this, but D is just the strength of discrimination between what would be considered noise. So a false alarm, a miss, maybe. A miss. And signal. So that's what D represents. However, half of D, or D half, is special because it's essentially saying that, well, maybe this has to do with the variance assumption here, but D maximizes the probability of correct classification when the signal and noise ratio are equally likely to occur. And part of that is because if discriminability is centered on, if the signal distribution is centered on D, the discrimination, then the half of D should also be half of the noise distribution if noise is centered on 0. So this is the, like, when noise and 0 are equal to one another, here is the decision criterion strength. However, in data, we see that this criterion K is what actually represents someone's decisions. Right? So when someone chooses, based on the number of hits one gets, so the yeses here in this binary, that's going to give us some value of K, where K can fall on to the left or to the right of this ratio or balance between signal and noise. And the difference between the K, so the actual criterion for choice, and the balanced one, is a bias term, so C. And from K, we also can derive the proportion or probability of a hit and the probability of a false alarm, represented by the tail of the distribution for noise and the cumulative distribution or area underneath the curve for values above and at K in the signal distribution. So all of which revolve around sort of extracting information from these noise and signal distributions. Sweet. So what does this look like when in a graphical model then, right?
Right, so what's useful about just reading this little paragraph here? Here's what these parameters represent. So this model is useful in that it gives us psychologically meaningful parameters, and that's part of its value, part of its utility, and probably part of the argument one could make for using signal detection theory over some other approach for modeling task data that involves choosing between two options, is the interpretation of the parameters. However, one could make the case that there are better models that also get at the same sort of information you're interested in. But like I said, I don't know. Not an expert. Yet. So here, then let's take a look at the graphical model. So D, as we said, was discrimination. So it's this center point in the signal distribution. And we're saying it's Gaussian and half. I don't know if that is precision or not. We'll find out. C, then, so the difference between K and D over 2 is distributed as Gaussian as well. And that's representative of the bias. So we have discriminability and bias. And now we have our hit rates, which is the cumulative density of 1/2 D minus the bias. So if we take away whatever bias we have in the distribution, then 1/2 D. We're trying to capture this. So 1/2 of D, 1/2 of D is here. Minus C. D. Half D. False alarms. Negative 1/2 D is the other side, minus C. Okay. I don't see this yet visually in my mind, but I did find this sick GIF. Check this out. So here is essentially what's representative of differences in discriminability. So as D increases, we get increased hit rates and decreased false alarm rates. So as our stimuli are more discriminable from one another. Right. And then here is what differences in bias look like, where when we're at the middle, we have no bias, equal proportion, with some proportion of false alarm rates. Though as the criterion moves, so as K moves from D over 2, we can see it could either increase the hit rates, the probability of hit rates, decrease the false alarm rates. So very cool. Very cool. It's like a nice shiny app I found. Okay. Let's open the signal detection theory script. Let me find the... Here we go, signal detection theory. Oh, we got quite the amount of data here. And we'll set it as the working directory. And let's get this started here. First, I'm going to put on a little jams. All right. In the words of one of my favorite statisticians or quant folk, Patrick Curran, we're cooking with gas now. Now I got my jams. So let me open up the signal detection theory script. Looks pretty simple. Cool. All right. Let's take a look. So for each K, it doesn't look like we have subjects here. Trying to look what K is. It looks like we have a whole group of people. We have hits. So we have yeses and nos. I think, let's see. Right. So you have the 4 blocks. You have to think of the 4 blocks. So if you have yeses and nos, and then you have like congruent and incongruent is the way I'm thinking about it right now, where hits are congruent, false alarms are incongruent. But it's almost like a double incongruent now I think about it, right? Because if you get no correct, then that is what would be called a correct rejection. So it's cases. So cases could be like subjects, maybe. 4 values for each. I see now. Excuse me. Hits. Right, so you had 200 trials in total for this first one, right? Mm-hmm. So this is 3 different data sets. I got it now. 3 different data sets, each of which have some distribution of trials, where we have 20 trials for the second one, 20 trials for the third one, and 200 trials for the first one. And they are distributed in terms of like what's representative of a yes and a correct rejection as being 100 trials and 100 trials for the first one. So for each of these cases, so for each of the data sets here, we're going to model the hits and false alarms rates as binomial distributions with these hit and false alarm rates. And in this case, S and N. So for the first case, S and N are equal to one another, right? S. Oh, these cases, S and N are equal to each other. So then we can parameterize such that we get equal variance. This is hierarchical, right? In the sense that parameters to get parameters. So we use this cumulative density where we take the posterior of D minus our bias, so discrimination divided by 2. So that is our criterion minus the bias. That's going to give us here the rate. And then false alarm rate is measured by the negative of this, so the inverse of the first term. And then we set some uniform priors. Though, one interesting thing about this, it seems as the priors are different from one another. So we have to think about how that might bias our results, or why we would want to choose different priors for the discrimination and bias terms. And notice this particular parameterization where you can do these maths that just are like negative di divided by 2 minus bias. Those only work when the variances are the same, right? So I wonder what they do when the variances are different. We'll find out if they do it here. But in the R code, here's the data as we were looking at before. That really, so we have 3 data sets we're going to be looking at for this first metadata set, right? And H is the hit rate, so it's going to be equal to H. So H is the hit rate across all of the cases, false alarm rate across all the cases. MI is the missed something. What's it called? a miss. And then we have correct rejection. So we have these 4 components. And from those components, we can derive S and N as well. We initialize the parameters that we set priors for. So discriminability and K here, or C is the bias. And now we're interested in these 4. And now we just extract D for, so this is extracting discrimination or discriminability from each, extracting bias from each, extracting hit rates and false alarm rates. And then we just plot it all. And that gives us this. So if we go and look at this, that first data set where we had 200 observations, the first visual thing we can observe is just the variability surrounding the options for the red distribution here is quite tighter. And part of that is because the confidence in our estimates, or the influence of the likelihood, given the sheer number of observations, at least with respect to distributions 2 and 3, which are based on, I believe, 10 observations, though with different rates. 20 observations, sorry. So 20 observations. So here, discriminability between the signal and noise is lower in these 2 distributions and higher in the blue one. Why higher in the blue one? Well, if you see, we only have data observing the difference at 10, right? So we're getting essentially like perfect accuracy on identifying signal and noise in the 20 trials here. So that makes sense why we have such high or inflated discriminability here with respect to the other ones. In terms of bias, then, you notice how we have a symmetric distribution on 0 for bias for the blue distribution, and part of that is because there's no bias. It's the criterion is equal to d over 2, right? The d over 2 is equal to the balanced ratio. And then negative C's over here reflect negative values of C correspond to a bias saying yes. So we have yes bias, slight yes bias for these, but that there seems to be a large probability of this also being equal to 0. And we can see the more yeses. Here's the hit rate for, here's the probability of the hit rate. And the probability of false alarm rate is essentially near 0 because we have perfect accuracy. Hitting is very, very high, so hitting the correct answer is high. So you can see across these 2 distributions the impact of sample size and then the impact of accuracy. Yeah. False alarm rates chance. You can also print the samples. Note to me, I look forward to using a new package soon. I've had it on the back burner, like on my tabs, but there apparently is this nice package that interfaces with ggplot that can be used for outputs, objects from Winbugs and Jags specifically, rather. So just as we have sets of packages that interface nicely with Stan objects, there are some packages that have been made to interface with Jags, which I want to try to implement. And you know what? No time's better than now. Let's see if they're on CRAN. They're on CRAN. GGMCMC. So let's see what we can do. Okay, let's see what the GGMC gives me for just giving it samples. Oh. Let's try GGS histograms.
looking for the tool.
Looks like I have to do this. Seriously? So F is either an MCMC list object with samples from JAG or an MCMC object with samples from MCMC pack. Looks like I can't do this right now. Alright. Alas. Some other time. Questions. Do you feel that the priors on discriminability and bias are plausible a priori? Why or why not? Try out some alternative priors and study the effect that this has on inference. Like I said earlier, I was curious about this. I guess I just do this. So what if the priors are the same? Well, yeah. Okay. So in the cases where we have 200 samples, it's not really impacting. Nice around 0 for those extremely diffuse. So it matters to an extent. It looks like the priors are definitely changing the distributions for these smaller data sets, but it's not clear, at least as long as we're not talking about very extreme cases, it's not clear how distributions are being impacted. For the large sample one. Oh, unless the priors are like ridiculous, like I was writing before. What would be another instance of an informative prior for a Gaussian distribution, or another uninformative prior? So, something like. Holy smokes. I don't know what I did. Wow, those false alarm rates are wild for these priors. What this is telling me also is just how important it is to have information about what's not a hit, because it looks like many of the cases for the posterior distribution for the third data set where we have perfect accuracy, we are very sensitive to, or at least discriminability and bias are very sensitive to the prior. In fact, reliant almost on the prior, because if I did perfect, then the discrimination is just representative of how we did, or what we thought how we did, right? Our prior beliefs about what was discriminable are spot on because we got complete accuracy. So the discriminability in this case would be highly reliant on what our beliefs before were. While since there's no bias, we would assume, as we saw, centralized around 0. But it's very shallow, so if we had more observations, it would increase. So let me do 100. Very discriminable. So we increase the data set so that now it matches the same size as the first data set, but we have perfect accuracy. Now we're getting 0. We have this symmetric distribution of bias with its maximum likelihood at 0. And then very, very high discriminability with respect to the other distributions. And that's also reflected just in the extremely high hit and false positive, or extremely low false positive rate. Yeah. Okay. What were the priors before? 5 and 2. Increasing the potential variability and the discriminability shifts the hit rate and false alarm rate so that they have longer tails, it's becomes increasingly more probable that not all hits are, not all trials are hits, because we have additional variability in discrimination ability. Yeah. That makes sense. The current priors are saying that, so discriminability, lower variability. So when you can identify a hit rate, a yes, it's a hit. Yet a more diffuse prior for the bias. Interesting. That's the question. Keep it through. All right. Leonard Crispin Vetter report data on the recognition memory of odors. 3 groups. Group 1 had 18 subjects, all with positive HIV antibody tests, and counts and CD4 counts. So measure strength of the immune system with a normal range being here. So when we're talking about strength, when they say the word strength here, it is reflective of this sort of unidimension, signal noise. That's where my mind goes for that. So group 3 had 18 subjects and functioned as a control group. Odor recognition tests involved each subject being presented 10 household common odors, memorize them. 30 seconds each between each presentation. After an interval of 15 minutes, a total of 20 odors were presented. So 10 household, 10 other odors, constant or equal presentation within each subject. 15 minutes total. So we have the 10 odors, and then we have 10 other odors, and they're randomized. And we had to choose between old and new. So signal here would be identifying an old when it's an old, right? Signal detection data results in 12.2. Here. Where these are hits. Correct rejection hits, and then the other terms. Analyze these 3 sets using signal detection theory to infer the discriminability and bias of the recognition performance for each group. What conclusions do you draw from the analysis, if anything? What can you infer about individual differences between subjects in the same group. Well, I already know that it's less likely I'm going to be able to infer individual differences, at least without even looking at the problem, because the current parameterization of the model assumes equal success rates across subjects for a given group. So it looks like I'm able to just say dataset 2 here. Sweet. But let's look at this. So this is what we were just talking about, equivalent to here in this table. So 1, 2, 3, 4. 1, 2, 3, 4. The total trials across all the subjects, right? It's interesting that we're not accounting for individual variability here, variability in the data source, right? So this is not reflective of that, but you can imagine a larger matrix that was sort of long format and had this indicator of like the data set it was from and the subject it was from. That way we'd be able to make some discernment about individual differences in each of these propensities, but at its current scale or representation, it's not possible, I think. Or they would be the same. I have no subject information here. I don't know where these values come from. So in terms of correctly identifying the old order, we've got these 3 rates, and then correctly identifying the new order, we have these rates, and then we have these rates for not correctly identifying one, and instead identifying the other. Let's see the size of the data. $360 trials. 360 divided by 2 is 180. Then 180 divided by 18. 10. Just like what we said. 10 smells. 10 smells. 10 new smells. 10 old smells. Within subject. Across 18 subjects. For a total of 360 trials. In the first 2, we have 180. Last one, we have 190. Okay. And let's take a look at this. So we have a control group in red, and we're using the same priors before. Control group in red. And then we're looking at the potential difference in discriminability with respect to a control group. So it doesn't look like there's any bias across any of the measurements in the sample. Let's look at right. So the bias looks like it's all over the place. It could be potentially 0 for each of these data sets. Discrimination, though, it looks like more discriminability in the data set 1, which is the control one, and then less discriminability between odors in the 2 data sets that are subjects, right? That are subjects with HIV or something. Was it HIV? HIV antibody, but so something wrong with, but we're talking about weakened smell something like that. Anyway, these folks weaken smell. And so less in discriminability, though across two data sets, it looks like it might be the case that this is similar to the sorts of discriminability we would tend to see in the population for this sorts of task, given that these distributions are so similar to one another for these priors. And it looks like, on average, people tend to perform pretty well across the data sets at this task with a hit rate of about 0.8. So identifying smells is easy. And then we see, though, this sort of stagger in the discriminability, in the false positive rate. So choosing the wrong smell increases not increases, but is higher probability in the second group, relative to controls, it looks like. And what is special about the second group? So they just have less CD counts. So really, really low CD something counts seems to be impacting olfactory sensors here, where the average range is like 300, 400 or something it said. But as you decrease in those olfactory sensors, it seems to be impacting your ability to, or it seems to be impacting the likelihood that you're going to identify a smell incorrectly. But not the probability of identifying a smell correctly, right? Which is interesting to think about, that those two things, while being related to one another, are sort of different from one another, and they might be like challenging one another. So part of this difference here in false alarm rate might be due to this difference in decreased ability for discrimination in our second group with the lowest olfactory skill set. So I'd say that's the insights I would take away from that study. That's fair. I could try some different priors here. Try one. And it doesn't look like at 200 that doesn't look like at 200 or 380 or 60 samples, whatever we have, that we're changing or the priors influenced that much. That's true. It's like fairly diffuse. Yeah, even this. So because the sample size is so large, it looks like we have invariant posterior distributions with respect to a range of possible prior distributions here. And so we're getting similar results here. So we can be a little more confident about the conclusions that we draw based on just looking at the range of possible distributions for our priors. In this case, we seem to be okay across the range that I considered there, though you could, of course, look at other values as well. But that seemed to be sufficient. No. So you can't infer anything from people from the same group. That's the niche and the giddy up here for this problem. So moving forward, perfect. Hierarchical signal detection is exactly the sort of framework we need to incorporate into the model if we want to, moving forward, account for how subjects from various, with various, what do they call them? CD4 counts, how within a given group of subjects, the discriminability and bias could be different. So it might be the case that in our particular subject pool, for the low CD4 count, we have some subjects who are driving the discriminability results here. Maybe. Imagine that across rarer conditions, we would see increased variability in the possible patterns of responses. So what does that mean? That means that in group 2, in group 2, we would see more or increased variability in discrimination, while in the control group, they're probably alike one another. Unless, well, that's not true. Because the olfactory recognition task, people could, in that particular group, could just be impacted because of this cell count thing, or a variety of other potential covariates that might be at work here across the 3 groups. But in this case, because they talk about cell counts, we're going to presume that it's performance or variability in performance across the groups is due to these cell counts. Like I said, because, I mean, we don't have there's a lot of unobservables here in terms of additional covariates, but. So let's take a look at a hierarchical structure then, right? Well, we got time, right? Well, we don't have time, but we could at least break down the model. So here. What does this look like it's doing? So instead of I here representing differences across studies, right? So before we were talking about differences across entire groups of subjects. But now if we go down to this model, oh, am I missing something? Let's see. Yeah, I was data sets before. Now we're going to look at individuals. And part of me wonders then that, well, I guess that's not interesting. But it sort of, I mean, before I even move into this, one thing that comes to mind would be cool to see would be some sort of latent mixture approach where we had some indicator that represented being part of one group or another, and in this case, it would be the HIV counts, where could we predict if you had high or low HIV counts based on the characteristics of your data, right? So these success rates and false alarm rates and discriminability terms, like, is that sufficient in order to make fairly
for us to group people into the correct, groups. That might be a model we can play around with, actually. But just looking at what we have here then, we're doing that same sort of hierarchical structure that we did yesterday for the memory retention example. Just to, remind you, get it, because we're talking about memory here, is we saw these two parameters within subjects, and for this we could develop this hierarchical structure where we said that these each of these parameters were distributed from a Gaussian distribution with mu and lambda here, precision. And this was baseline and memory decay. But now, in this case, we're looking at bias and discriminability, and we're saying that bias and discriminability can also, individual scores can be pulled from these distributions of discriminability with variance and mu, or precision of mu. And we're going to use relatively uninformative priors here to see if we can get some estimations, and we're jointly estimating them, okay? Yeah, so same priors across each of the terms here, which, like we was mentioned briefly in the one question, that might not be the best approach, right? Was it? No, that's appropriate here. But you could imagine how, depending on the characteristics of the task, you would potentially want to change the distributions across these parameters, because it might just be a characteristic that people tend to get things more right, or get the correct answer because of task difficulty or something. So now in this case we have samples of each of the correct, or the signal and noise, right? And we have rates of hits and false alarms, which give us these success rates for the hits we observed, or the data we observed. And then from that we can describe these fixed effects for bias and discriminability, where individual scores are, or we get these fixed effects up here, right? Yeah, where individual scores are derived from these distributions. So let's open this script, or we got a couple. We don't have that much time. Let me read over some of the rationale then. Apply to a different problem where individual subject data is. And that was another thing. We didn't have individual subject data before. So this allows us to do hierarchical extension. Subjects have different discriminabilities and are drawn from a Gaussian level. Okay, the data come from the empirical evaluations of a conjecture made by RIPS, inductive and deductive. So this dude was like, hey, maybe inductive and deductive reasoning can be understood as a unidimension of sort of signal and noise discriminability, or it could be understood in a signal detection theory framework. So the strength of an argument. I see. So the discriminability of an argument has to do with how good it is. Where a high signal or high discriminability is reflective of a good argument in this conjecture. So the criterion separates weak versus strong arguments, and invalid and valid arguments. So we're looking at 80 subjects,
and each subject is going to have 8 arguments. That means between subject design, such that 40 subjects were asked to make induction questions, and 40 subjects were asked to do deduction questions. Okay. But you can imagine this design being also within subjects too. So we could identify, is there a difference in discriminability across the 2 types of arguments, which I guess that would be, from a cognitive perspective, interesting to know. Like on average, is it a case that, I don't know, inductive arguments are somehow like easier to characterize because the arguments tend to be stronger based on people's ability to discriminate. We'll see. So these data hit rate, individual differences among hierarchically individual discriminabilities come from Gaussian distribution. And then here we go. And this is fairly standard. K here is the data sets. Or if it's the data. No, it's people, but it's my alarm for class is going off. So tomorrow we'll get started with doing the hierarchical signal detection theory example where we identify individual differences for these parameters. And we're going to learn about potentially differences in inductive and deductive arguments across subjects. That'll be fun. Sweet. All right, thanks. I gotta go. But today was awesome, and it was really fun to talk through this example and play around. I'm going to try to figure out that MCMC thing. I think it would be cool to figure out some way to do easy visualizations, quick visualizations for JAGs specifically. I haven't figured out how to do it without writing some code. I could write out some functions. I could spend some time actually writing out some functions that might be useful for these examples. But all right, we'll see you tomorrow then.